Hi everyone and welcome to this short video about vector spaces. In this video we will learn what a vector space is and talk about the concept of linear combinations. After that we will talk about the linear span of a set of vectors and the spanning set of a vector space. Finally, we will also learn what a linear subspace is and how you can check for that. Throughout the video, there will also be some exercises and examples to make the theory more understandable for you in practice. With that being said, let's start. Last week, you have already learned that vectors belong to vector spaces. Now, the time has finally come to introduce you to the real definition of a vector space. You've already learned how you can calculate with numbers, but with vectors, we usually want to represent higher dimensional spaces. Therefore, we need to make sure that we can use our mathematical operations so that we can add vectors together or multiply them with scalars, like you've learned last week. This only works under certain conditions, and the conditions are that we need a vector space, which is the space we operate in. Let us go through the definition of a vector space together. Let K be a field and V be a set. We have the vectors u, v, and w, which are elements of the set V, and we have the scalars r and s, which are elements of the field K. Now, we call V a K-vector space, or also said V is a vector space over the field K, if the following axioms hold. The first one states that u plus v is equal to v plus u. So the direction of the vectors, when you add them, is not important. It's equal, whether you say u plus v or v plus u. And this is referred to as the commutativity of addition. The second one, which is the associativity of addition, states that u plus v in parentheses plus w is equal to u plus v plus w in parentheses. So here it doesn't matter in which order you add them. Now, the third one states that v plus 0 equals v, which means there has to be an identity element for the addition. And the 0 here just looks like a 0, but actually it means that there has to be a 0 vector. So some kind of vector that has zeros everywhere, so that we add them. If we add it to the vector v, we still have the vector v. So this is the identity element of the addition. And the last axiom that has to hold regarding addition is that we need to have an inverse element, which means that for every vector of our vector space V, there has to be another vector, let's call it Z, that is also an element of the vector space, so that if we add these two vectors, we will get the 0 vector. So for example, 1 plus minus 1 would be 0. And you can imagine this in higher dimensional spaces as well. So for the addition, there needs to be an identity element and an inverse element. And there has to be this commutativity and the associativity. But now onto the multiplication, because there we also have 4 axioms, which are written in orange here. The fifth axiom states that 1 times v equals v. So there has to be an identity element for the multiplication as well. There had to be one for the addition already, which was kind of like a 0 element, but for the multiplication it needs to be a 1, so that it would yield the same vector again. If we multiply the scalar 1 with the vector, that would be the vector again. And the sixth rule is the associativity of scalar multiplication. So r and s are scalars here, and v is a vector. And now the direction of the multiplication should not matter. So it doesn't matter if you first in brackets multiply the scalar s with the vector v, and then you multiply it with the scalar r, or whether you multiply r and s, so the scalars together first, and then multiply them with the vector. The last 2 axioms that need to hold for V to be a vector space are regarding the distributivity of scalar multiplication. And the first one is about the distributivity of scalar multiplication with respect to vector addition, and the second one is for the distributivity of the scalar multiplication with respect to field addition. But let's start with the first one, which is axiom 7 here, which was about the distributivity of scalar multiplication with respect to the vector addition. So we have two vectors, u and v, and we have the scalar r. And now it's the same whether we add the two vectors in parentheses first and multiply them with the scalar r, or whether we take it apart and have the scalar r times u plus afterwards the scalar r times the vector v. So the second and the last axiom here is the one that was about the distributivity of the scalar multiplication with respect to field addition. So this means we have two scalars from our field now, which are r and s. And now it shouldn't matter if we add them first, r plus s, and then multiply them with the vector v, or whether we take it apart. So whether we have r times v and then afterwards add s times v. And that's already it. So for a vector space, we have to have all these axioms, so they all need to hold, and then and only then V is a vector space over the field K. So to make this more clearer, if we have a vector space V, this means that all the operations need to hold, all the axioms need to hold, and then we can use the usual operations. And if we say that the vector space is over the field K, this means that the scalars we can use for the scalar multiplication have to be from this field, so from this set of numbers. But let's move on to the next topic now. Last week, the term linear combinations already came up when we talked about linear independence of vectors. To make this clearer, let us go through the formal definition together. Let K be a field and V be a vector space over the field K. We have the vectors v1, v2, and so on until vn, which are all vectors from the vector space V. And we have the scalars s1, s2, and so on until sn, which are elements of the field K. Now, if we combine them in the following way, s1 times v1 plus s2 times v2, and so on until sn times vn, we call this vector, so the vector we created with this linear combination of the vectors and the scaling of these vectors with the scalars, a linear combination of the vectors. So in other words, a linear combination of a set of vectors means that we linearly combine them in the sense that all the vectors are added together and we additionally weight or scale them with the scalars. Linear combinations of vectors are a big and important topic when it comes to linear algebra in general. For example, if we check for linear independence, we precisely check for a linear combination and want to find the scalars with which we can linearly combine the vectors to produce the zero vector. But also when we want to create any other vector by a combination of other vectors. Generally, in such cases, we are interested in the scalars from the linear combination which yield a specific vector as solution. Let us go through an exercise together to deepen the understanding of linear combinations. In the following exercise, you are given three vectors from the vector space R3, so a three-dimensional space of the real numbers. The task is now to check if there's a linear combination of the vectors v1, v2, and v3, which produces the vector v4. As a hint, you can solve this in a system of linear equations. If you already feel quite comfortable with this, you can skip the task, but I would say that it is a good training not only for understanding, but also for the exam soon. Here you can see the solution to the task. You always start by filling in the vectors as columns in the system of linear equations, and you write the solution vector on the right side behind this vertical line. Now, the goal is to get the representation that only has ones in the diagonal and zeros everywhere else, because then you can simply read the solution. To get there, you can apply the usual rules of systems of linear equations, which you have learned last week. If you're not familiar with this yet, you should go back and watch the video. I won't go through all the steps in detail, but here you can see all the steps with short descriptions about what happened in gray. It starts on the top left, then downwards, then top right, and then downwards again, if this is not clear. And if you want to go through the steps in detail, you can pause the video now. And finally, after some calculations, you will come to the following solution. Indeed, the three vectors v1, v2, and v3 can be linearly combined to produce the vector v4. The scalars for this linear combination are 3 for v1, 2 for v2, and -4 for v3. So to write this properly as a linear combination, you would have 3 times v1 plus 2 times v2 minus 4 times v3 equals v4. Let us continue now with the concept of linear spans. Again, we have a vector space V over some field K. And we have a set of vectors v1 until vn, which belong to our vector space V. Now, if every possible vector v from our vector space V can be expressed in the form v equals the sum from k equals 1 to n of sk times vk, with sk being an element from the field k, then we call these vectors vn until vn a spanning set of the vector space V. And then we also say that the linear span of these vectors, so the linear span of the spanning set, is the vector space V. This sounds more complicated than it actually is. Let us look at the formula again. What we see is a sum, and inside of the sum we have vectors, which are weighted by scalars. So you might recognize this already. This is a linear combination of the vectors v1 until vn. And what we want to do is that we want to be able to produce each possible vector of our vector space V with this specific set of vectors in a linear combination. If this is possible, the vectors are a spanning set, or also called a generating set. And we say that the linear span of a set is the vector space that it produces with linear combinations. Regarding terminology, there are several terms here that you might encounter. Linear span is referring to the same thing as the linear hull, or just span. And the term spanning set means the same as generating set in this context. I want to continue talking about linear spans for a bit more, but will introduce a slightly new notation now. You've just learned about the terms spanning set and linear span. The terms are quite intuitive here. The spanning set spans the vector space, so all vectors in this space can be reached by linear combinations of the vectors from the spanning set. We write span of S, which means the span of the set of the vectors S, for the span. And what we mean by that is the set, therefore in curly parentheses, of all possible linear combinations of vectors from the set S. So this means that the span of a set S is the vector space it spans. Definition-wise, you can say that the linear span of a set of vectors is the smallest linear subspace which contains this set. What a linear subspace is will be explained in a second. But basically here we mean that the linear span is the smallest vector space that contains the set of vectors, and hence the linear span of a set of vectors is a vector space. Here I want to show you some examples. In the first one we have the three vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And the set of them is a spanning set of the R3, meaning that the linear span of these three vectors is equal to R3. This means that we can reach any point in the vector space R3 by linearly combining the three vectors from our example. Here this is actually quite easy because each of the vectors only contains information about one dimension. Therefore, finding the scalars for a linear combination that produces a specific point or vector is super easy. Let's say you want to produce the point 3, 4, 5 by linear combination from the three vectors here. By just looking at it, you can see that the scalars would also simply be 3, 4, 5. So to sum this up again, the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 are a spanning set of R3, and the linear span of them is therefore R3. But now onto the second examples. Here we have the 4 vectors 1, 2, 3, 1, 1, 1, 2, 2, 4, and 3, 6, 7. They are also a spanning set of R3. This means that we can also hit any point in the R3 vector space by linearly combining these vectors. So the linear span of these vectors is R3. While here it is not so easy to find the correct scalars to produce a specific vector by a linear combination, it is still possible, and that's why it is also a spanning set of R3. So this example was to make it more understandable that a vector space can have many different spanning sets. As long as the linear combination of a set of vectors can produce each vector from a vector space, the set of vectors is a spanning set of this vector space. But this is not the same the other way around. A set of vectors only has one linear span, which is the vector space it spans. Now we talked a lot already about spaces and spans. Let us move on to linear subspaces now. As the name already suggests, a linear subspace is some subpart or space that belongs to another vector space. Let us go through the formal definition together. Let K be a field and V be a vector space over the field K. Now we have U, which is a subset of the vector space V. By subset, we therefore mean a set of vectors which lays in V. Now we call this subset U a linear subspace of the vector space V if the following 3 axioms hold. First of all, the linear subspace must contain the 0, or the respective 0 element, so the 0 vector of that dimension. This is crucial because we need this vector for U to be a proper vector space anyway, if you remember the definition of a vector space that you learned in the beginning of this video. It is the identity element of addition. Therefore, if the 0 vector is not contained in U, we directly know that it cannot be a linear subspace of V. But there are also 2 other rules that need to hold. The second one is that if we have 2 vectors from our subset U, let's call them U and V, then the addition of these vectors, so U plus V, the resulting vector, must also be an element of U. The last axiom that needs to hold is that if we have a vector from the subset U and a scalar lambda from the field K, so the field over which our vector space V was defined, then the scalar multiplication of them, so lambda times U, must also be an element of the subset U. If and only if all of these 3 rules hold, then we say that U is a linear subspace of V. Otherwise, it is just a set of vectors from V, but not a linear subspace of V. These 3 rules are very important and you should try to remember them well. So all it needs for a linear subspace are the 0 element, vector addition must work in the subset, as well as scalar multiplication. But because this is so theoretical, let us apply this in practice now. Here I have 2 examples prepared for you. You can check whether they are linear subspaces of R2 with the help of the axioms from the last slide. Generally, as soon as you find a contradiction, you can stop, because then you already know that it cannot be a linear subspace. For the first example here, U1, you have the definition that it contains all vectors AB from R2, for which it holds that A is equal to B squared. So, for your understanding of this definition here, this means that it would, for example, contain the vector 4, 2, because 4 is the square of 2, or the vector 25, 5, because 25 is the square of 5. The second example here is defined by all vectors from R2, for which the relation A equals 5B holds. So for example, 5, 1 would be a vector in U2, or 10, 2, because the first value, A, has to be 5 times the second value, B. You can pause the video now to calculate on your own the two examples. So you do need to check for all the three axioms whether they hold. We will go through the solutions and steps together in a second. Here you can see the solution for the first exercise, so for the first set U1. And we want to check whether U1 is a linear subspace of R2. U1 was defined as all the elements AB, which are elements of R2, for which it holds that A is equal to B squared. So now we need to check whether the axioms hold. The axiom 1 was the one that told us whether the zero element is contained in our set or not. And if you remember, the zero element has to be element of the set in order for it to potentially be a linear subspace. So the zero element in this case would be the vector 0, 0. Now to check whether this lays in U1, we need to check if it fulfills the condition to be in U1. And the condition was that A equals B squared. So 0 would have to be the same as 0 squared, which is obviously true. Therefore, the zero element is an element of U1 and the first axiom is fulfilled. And now we will continue with the second axiom. The second axiom was about vector addition, and it told us that if we have two vectors that are elements of our space of U1, then the addition of these two elements also needs to be part of the space U1. So what we do is that we take two elements now and we write them as AB and CD, and they are both parts of U1. Now with the rule that A equals B squared, we can rewrite them as the vectors B squared B and the vectors D squared D. And now if we add them, this would yield the vector B squared plus D squared, B plus D. And this is what we have to do in the rule of these axioms. So we have to add them and have to check whether the resulting vector, which is B squared plus D squared in the first dimension and B plus D in the second dimension, whether this vector is also an element of U1. So for it to be an element of U1, the equation would still need to hold that this equation that is read so that A equals B squared. So in our case, this would mean that B squared plus D squared would have to be the same as the square of B plus D, so because this is the lower element. But this means that B squared plus D squared would have to be equal to B squared plus 2BD plus D squared. And this consequently means that 0 would have to be equal to 2 times BD, but this is not always the case. There can be examples where this does not hold. And therefore, U1 is not a linear subspace of R2. And you can also show this via a counterexample if you want to. Because if you take two vectors that are part of U1, for example, 1, 1 would be 1 because 1 is the square of 1, or 4, 2 would be 1 because 4 is the square of 2. So you have these two that are for sure elements of U1, but now if you add them, you would get the vector 5, 3, but this vector 5, 3 is not an element of U1 because 5 is not the square of 3. And this is also enough, so this counterexample way would also work. And now we can stop with this example here because we already showed that U1 is not a linear subspace of R2. Let's move on to the second exercise. Here you can see the solution for U2, so where you had to check whether U2 is a linear subspace of R2. And I will also go through this with you together and explain all the steps. So U2 was defined as all the vectors AB, which are elements of R2, for which it holds that A is equal to 5B. Now, to check whether it is a linear subspace of R2, we again want to check for the three axioms, and if they hold, we know that it's a linear subspace. The first axiom was the one about the zero element, and again, we just plug in the zeros in our formula and check whether it holds. And this is true, so we know that the 0 element is an element of U2 because 0 is equal to 5 times 0. So the vector 0, 0 is indeed an element of U2. For the second axiom, which was about the vector addition, we do the same as on the last slide, on the last example. So we imagine that we have two vectors from our set U2. And we call one of them AB and the other one CD. And now with the rule of the definition of U2, which was the one written in red here, which is A equals 5B, we can rewrite them. And therefore the first vector AB can be rewritten as 5BB, and the second one CD can be rewritten as 5DD. And now we add them, and what we will get is 5B plus 5D, and then B plus D. And now we want to check again whether this is an element of U2. So whether the equation A equals 5B, whether this holds, the red equation. And what we will see is that this indeed holds. So 5B plus 5D is equal to 5 times B plus D. And therefore this is true. The second axiom holds. Now we only need to check for the third one. The last axiom is about scalar multiplication. So we take a vector AB, which is an element of U2, and we take a scalar lambda, which is an element of the field R. And now we perform scalar multiplication. So we multiply lambda with the vector AB, which yields the vector lambda A lambda B. And now we want to check whether this is an element of U2. And we can do this again with the equation from above, the red one, so A equals 5B. So we need to check whether what we have written in the first dimension, which is lambda A, is equal to 5 times the thing in the second dimension, or whether there is some kind of contradiction. But in our case, it would be lambda times A is equal to lambda times 5B, which is the same as 5 times lambda b, and therefore this is true. And this means that U2 is indeed a subspace of R2. And this is already it for this video about vector spaces. By now you should be familiar with the general concept of a vector space and what it means that a vector space is defined over a field. You should also be familiar with linear combinations and how to calculate the scalars for a linear combination that produces a specific vector as solution. What the terms linear span and spanning set refer to should also be clear by now. And finally, you should also know what a linear subspace is and how you can check for it. I hope you liked this video and see you again next time!